We'll start this review section now by doing some fluid questions. And we'll begin with a question about a helium balloon. So in this question we have an empty balloon. We know the mass of the balloon, we fill it up with helium. The thing we have to remember here that while helium is very light, it still has some mass. As we blow it up, the radius of the balloon goes to 10.5 centimeters. It doesn't specifically say here, but we're going to assume a spherical balloon. Part 1, what is the weight of the helium in the balloon? So we're assuming a spherical balloon. It's full of helium, so we know that the weight of the helium is the mass of the helium times g. How do we find mass? Well, we know that density is mass over volume, so mass is going to be density times volume. For the volume, the helium is inside the balloon, so the volume is going to be the volume of the balloon times g. Volume of the balloon, why don't we find that off to one side, because I think that might be an important number as we go through the problem. Volume of the balloon is 4/3 times pi times r cubed. 4/3 pi, 0.105 meters. Always have to put things in meters here, don't forget to cube it. And for the volume of the balloon we get 4.85 times 10 to the minus 3 cubic meters. Okay, let's come back and use that to find our weight of our helium. Weight of the helium then is the density of helium that's given in the problem times the volume of the balloon and then weight is mass times gravity, 9.81 meters per second squared. Gives us the weight of the helium in the balloon is 8.51 times 10 to the minus 3 newtons. Now technically this is a vector and the direction of that weight vector would point down. Okay, part 2. What is the buoyant force exerted by the air on the balloon? So our balloon is in air. It's pushing air out of the way. Air is actually a fluid, so this balloon, when it's in air, experiences a buoyant force. We know how to calculate that buoyant force. So we know that buoyant force, FB, is the density of the fluid, in this case that's air outside, times g, times the volume of the fluid displaced, and in this case the volume of fluid displaced is going to be the volume of the balloon. We'll fill in our density of air, that's 1.29, times g, times our volume of balloon, which we found up here, then we put all that through the calculator. We get for our buoyant force 0.0614 newtons. As a vector, we know that the buoyant force points up, so that would be in the up direction. Third part of the question, when we release the balloon in air, does the balloon rise, sink, or remain stationary? Support your answer with calculations. So we have to figure out the motion of the balloon. Right off the bat, you might think that the balloon is going to float, because that's what happens in our everyday life. We know that balloons filled with helium will float. But this time, if we look at the mass of the balloon, it's 5.46 grams. I would say this is more massive than a balloon you might pull out of a pack to inflate for your birthday party. So I'm going to say right off the bat, even though most balloons do rise in air, because this balloon has such a big mass, I'm not really sure about this specific balloon. So support your answer with calculations. What that means is that we have to treat this like a Newton's second law problem. Let's draw the free body diagram for the balloon. Let's write down our Newton's second law, and then let's have a think about the acceleration. If the acceleration is positive, it will go up. If the acceleration is negative, it would go down. If the acceleration is 0, it would stay exactly where it is. Okay, let's figure all that out. First thing I'm going to do is I'm going to draw my balloon again. Now I'm going to put the forces on my balloon. I know that the buoyant force holds it up, and then the weight pulls downwards. The weight has two parts. The balloon itself has some weight, that's going to be mass times gravity, and the helium inside the balloon also has some weight. Okay, so there's our free body diagram. The sum of the forces in the y direction is the mass times the acceleration in the y direction. Here m means the total mass. That would be helium plus balloon. I'm not going to calculate that just yet because maybe I won't need it. I'm going to think about this side first. Sum of the forces in the y direction. So in the y direction, I've got my buoyant force minus the weight of the balloon minus the weight of the helium equals mass times acceleration in the y. Okay, I want to calculate this part next. So my buoyant force, FB, I already found that. FB was equal to 0.0614 newtons. Weight of the helium, I already know that part. That was 8.51 times 10 to the minus 3 newtons. What about the weight of the balloon? I haven't figured that out, but I certainly can figure it out. It's the mass of the balloon times g. The mass of the balloon is 5.46 grams, or 5.46 times 10 to the minus 3 kilograms, times 9.81 meters per second squared. Put that through the calculator, and the weight of the balloon turns out to be 0.0536 newtons. Okay, now I'll come back to here. My net force in the y direction, which is FB, 0.0614, subtract the weight of the balloon, 0.0536, subtract the weight of the helium, 8.51 times 10 to the minus 3 newtons, is minus 6.73 times 10 to the minus 4 newtons. Since my net force is negative, that means my acceleration is also negative. My acceleration would be what I got when I divided my net force by the mass. If my acceleration is negative, it means it accelerates downwards. That means it's going to sink. Okay, so there's part 3 answered. For our next question now, let's see which one we'll do. Let's do a question now about floating and rocks and buoyancy and all that stuff. So let's pick this question. Dr. Golding and Dr. Demeroff are afloat on a large flat block of ice. Doesn't look that flat, but that's what this is supposed to be. We know the volume of the ice and it's in a shallow pond. The two professors have a combined mass of 160 kilograms. What's the buoyant force exerted upwards on the ice? So let's draw a free body diagram. For our free body diagram, and I'm going to draw it right on our picture here, we know that we have the buoyant force pointing up, and we have the weight pointing down. For our weight has 3 parts. It's the weight of Dr. Golding, it's the weight of Dr. Demeroff, and it's the weight of the ice. Okay, so our weight has 3 components, both people and the ice. We know that the net force is going to be 0 because it's not bobbing up or down. So as we get started in part A, we'll say that the net force in the y direction is our mass, and that's going to be Golding plus Demeroff plus ice, times the acceleration in the y direction. Acceleration in the y is 0, so our net force is 0. So then we have for our net force, buoyant force minus our total weight, equals 0. So our buoyant force then, it's going to be the weight of Golding plus the weight of Demeroff plus the weight of the ice. Let's see if we can figure this out. The weight of Golding plus the weight of Demeroff is going to be the mass of Golding plus the mass of Demeroff times g. That part's okay because we know there are 2 masses combined, plus the mass of the ice times g. We don't exactly know the mass of the ice. However, we do know that mass is density times volume. And we know that the density of ice is 917 kilograms per cubic meter. We're multiplying that by the volume of the ice, 2.1 cubic meters. So we can find the mass of that ice. It's 1925 kilograms. Very, very massive ice. Okay, let's keep going with our equation. So now our buoyant force is the mass of Golding plus the mass of Demarov, 160 kilograms times 9.81 meters per second squared, plus the mass of the ice, 1925 kilograms times g, 9.81 meters per second squared, gives us a total buoyant force of 20,461 newtons. And of course the direction of that force is straight up. Okay, there's part A done. For part B, by reaching into the water, Dr. Golding and Dr. Emeroff pick up rocks of mass 5 kilograms and put them on the ice. How many rocks do they have to bring on board before the ice is just underwater? Okay, so now what we have to do for part B is let's draw a new free body diagram. So here's our block of ice. Here's Golding, here's Demarov, and here's a pile of rocks. In our free body diagram, we've got the buoyant force up, we've got the total weight down, so that's the weight of Golding plus the weight of Demarov plus the weight of the ice plus the weight of the rocks. I'll use R for rocks. So that's all those weights combined. And we've got our buoyant force up. So now we'll write down our Newton's second law that says that the net force in the y direction is the mass total, Golding, Demarov, ice, and rocks, times the acceleration in the y direction. What we know is that the ice is going to be just underwater. Okay, so it's not bobbing up or down, it's just sitting underwater. Acceleration is going to be 0, so our net force is going to be 0. Okay, so our net force is going to be the buoyant force, subtract the total weight, equals 0. So now our buoyant force minus mass of Golding plus mass of Demarov plus mass of the ice times g minus mass of the rocks times g equals 0. So now what I did here is I know my weight is the combined weight of everything. I grouped Golding, Demarov, and the ice all into one group because we already did that calculation and I didn't want to have to bother doing it again. So this whole number right here is 20,461 newtons. What I'm ultimately after is what is the mass of the rocks. I know every single rock has a mass of 5 kilograms. If I can find the total mass of the rocks, I know one has a mass of 5 kilograms, I should be able to figure out how many rocks we have. Okay, the next thing we need in this calculation is what is our buoyant force. So let's do that part next. For our buoyant force, now all of the ice is underwater. So my buoyant force, FB, is density of water times G times the volume of the fluid displaced, which is the volume of the ice. So that's 1,000 kilograms per cubic meter times 9.81 meters per second squared times the volume of ice, which is 2.1 cubic meters. Okay, let's grab the calculator. We'll just do that in the calculator real quick. 1,000 times 9.81 times 2.1. So our buoyant force is 20,601 newtons. Okay, kind of getting somewhere here now. So I'm going to put these things in my calculation and I'm going to figure out the mass of my rocks. So to carry on with my equation, I think I've got it all on the screen here now. So I've got my buoyant force, 20,601 newtons. Subtract 20,461 newtons equals mass of the rock times g. I just brought this one over to this side. So let's do this calculation on this side. Minus 20,461. Whoops. Not so great at calculator. 140 newtons equals mass of the rock times g. So we'll divide both sides by g. Meters per second squared. We get that the mass of the rocks is 14.3 kilograms. Okay, 14.3 kilograms is the total mass of the rocks. So the number of rocks we must have. If you did this calculation, each rock is 5 kilograms. So you would take your number and divide by 5 kilograms to give you 2.85 rocks. Now, you can't have 2.85 rocks. You can either have 2 rocks or you can have 3 rocks. How many do we have? It's got to be 2. If you put on 3 rocks, it would sink down even further and the whole thing would go more underwater and Golding and Demirov would get their feet wet. So in this case, you have to round down to 2. Number of rocks equals 2. Okay, and then part C, with the rocks on board, has the water in the pond risen or fallen? And support your answer. So for this one, this is a standard thing that we took our time and went through carefully in the lectures. When the rocks are on the bottom of the pond, in this case, they've displaced their own volume. Volume displaced equals volume of the rocks. When the rocks are off the bottom and they're on the ice junk itself, if you draw the free body diagram here, you'd have the buoyant force up, you'd have the weight down, you'd see that the volume displaced would be greater than the volume of the rock. When it's underwater, it displaces its own volume. When it's above the water, floating on a boat or a raft, it has to displace enough water to make up for its total weight. It has to displace more water. So therefore, when the rocks are on the ice floe, the water level rises because it displaces more water. If you're shaky on that, we kind of did a long bit about that in the lectures, and you can go back and go through it. Okay, there's that question done. Now in our fluid section, let's do one more. Let's do a manometer type question. In this manometer, we have oil. Just make sure the page is lined up. We have oil with a density of 600 kilograms per cubic meter. That's right here. The height of the oil is 41 centimeters, and the pressure of the gas in this chamber is 97 kilopascals. Outside in the air, the atmospheric pressure is 101 kilopascals. How much water is in this part of the tube right here? When we do these problems, what we have to do is pick 2 points, A and B. They have to be at the same height and in the same fluid. Point A, point B. When we pick 2 points at the same height in the same fluid, they have to have the same pressure. PA equals PB. Okay, let's see what both of those pressures are equal to. Pressure A is where the air meets the water. So the pressure at point A is very simple. It's just atmospheric. 101 times 10 to the 3 pascals. What about the pressure at point B? Well, the pressure at point B is a result of everything above it. And the things above point B are, we've got the gas on the very top, so we've got the pressure of the gas. We've got some oil contributing to the pressure, so that pressure is density of oil times G times the height of the oil. Then we also have some water on top of point B that also contributes to the pressure. Pressure of water times G times height of water. So things we know in this equation, pressure of the gas in the chamber is 97 kilopascals. Then we're adding on rho oil G height oil, so 600 kilograms times cubic meters, 9.81 meters per second squared. And then for our height, it's given in centimeters. We see we have meters here, so we have to put this in meters. And now I'm a little bit out of space, so I'm going to fill in here row water, just break down on the line, times G times H water, the number I don't know. Okay, I can put all these things together. So pressure A equals pressure B. 101 times 10 to the 3 pascals equals, I think I'm just going to do this part on my calculator. So 97 exponent 3 plus 600 times 9.81 times 0.41. So these two numbers added together give us 99,413 pascals plus 1,000 times 9.81, 9,810, with units of kilograms over meters squared times seconds squared times height of the water. Okay, so now what we have to do is solve for the height of the water. 101 times 10 to the 3 pascals, subtract 99,413 pascals, divided by 9810 kilograms meters squared seconds squared equals height of the water. Height of the water is equal to 0.162 meters or 16.2 centimeters. Okay, so that was all the fluid questions I was planning to go through.